Okay, so let's calculate the pH of strong acids. So when we're calculating the pH of strong acids, we assume that they dissociate fully. So this makes it really simple. Okay, you'll do pH of weak acids, and it's a little bit more complicated, but strong acids are fairly straightforward. So for monoprotic acids, such as hydrochloric and nitric acids, they dissociate one proton for every molecule of acid. Okay, so this means that the concentration, as you've seen just before, the concentration of the acid equals the concentration of the H plus ions. So, for example, the pH of the pH of a 0.25 moles per dm cubed of hydrochloric acid is H plus equals the concentration of acid, so that equals the same because that's the assumption we're making. So therefore, we can say that the pH is the minus log of 0.25. That's just the concentration of the acid. And that gives us a pH of 0.6. Because this is hydrochloric acid, that's sensible because that pH is in the strong acid region. If you're getting something like 13 or 14, something hasn't gone right because you can't get hydrochloric acid that's got a pH like that. So, always check your answer. The number has a meaning, so relate it back. So diprotic acid is a little bit more complicated, but you've just really got to watch out for it. It's not too difficult. Just be really vigilant when you get these types of questions. Sulfuric acid, what that does is that produces 2 H plus ions for every acid molecule. So sulfuric acid produces 2 H plus ions. So that means the concentration of the acid is 2 times the concentration of the H plus ions. Okay, because we're producing two times the amount of H plus ions. So for example, if we want to work out the pH of 0.25 centimeters cubed of sulfuric acid, then we have 2 H plus ions equals 1 acid molecule, the concentration of. So 0.25 moles per dm cubed of acid produces double the amount of H plus ions. So it's 0.5. Remember, you've got to do that first. Then all we do is we plug that into our normal formula and we get a pH. And again, the pH is 0.3. So that's to be expected because sulfuric acid is a strong acid. Okay, so let's look at calculating the pH of strong bases. So similar to strong acids, but what we're doing is we're calculating the pH of a strong base. We've got to assume that they dissociate fully, okay, which is the same as a strong acid, but we're dealing with a base instead. So for example, here's sodium hydroxide, which is a strong base. That dissociates fully into sodium ions and hydroxide ions. And most of these strong bases, these dissociate to produce 1 OH minus ion for every base molecule. So it's a pretty straightforward ratio. So it means whatever the concentration of the base is, will be the same as the concentration of OH minus ions that it produces. So to calculate the pH of a base, we still need the H plus ion. We still need that. But to get this, what we have to do is use that Kw expression that you've just seen before. So to work out H plus, we need to know Kw, and we need to know the OH minus concentration at a certain temperature. Because remember, Kw does change if the temperature changes. So once we know the H plus ions, or the H plus concentration, we can work out pH. So for example, if we calculate the pH of 0.15 moles per dm cubed of sodium hydroxide solution at 298 Kelvin, so that's the temperature. Kw, remember, has a value of 1 times 10 to the minus 14 unless it's specified otherwise. So first, what we're going to do is substitute the figures into the Kw expression. So the Kw expression is 1 times 10 to the minus 14 equals H plus times by 0.15. So 0.15 is your concentration, that's Kw. We then rearrange that expression to find H plus. So H plus is 1 times 10 to the minus 14 divided by 0.15, and that gets us 6.67 times by 10 to the minus 14. So that's the concentration of H plus. And then now we've got the H plus, we then look at our pH equation, minus log of the H plus, and then we get our pH of 13.18. Again, this is sensible because this is a strong base, sodium hydroxide. So that means that the pH has got to be somewhere in the region of 13 to 14, and it does come out with that. So make sure your answers are sensible. That's the key thing. If it's not, then go back and see if you can work out where you've gone wrong. Okay, so Ka, acid dissociation constant. So weak acids dissociate slightly. Now you'll use this formula when you're working out the pH of a weak acid. So the ones that we've seen there just before is a strong acid and a strong base, which is fairly straightforward because you can assume they fully dissociate. The problem is with weak acids, they don't fully dissociate, and so therefore it's really difficult it's a little bit more trickier to calculate the pH of that. So they only dissociate slightly in aqueous solutions, so we have to use another constant to help work out their pH values. So what we can do is, where with a strong acid, like I say, we can assume that the amount of H plus ions equals the concentration of H plus ions equals the concentration of acid. We can't do this for weak acids, and so we use this acid dissociation constant, which is Ka. And so for weak acids, they exist in this following equilibrium. So it's Ha, H plus, A minus. No different from any other acid, it's the same. It's the position of equilibrium which makes weak acids different to strong acids. So the first assumption we make when dealing with weak acids is that only a small amount of the weak acid, that's Ha, dissociates. So what we can assume is that the concentration of Ha at equilibrium, that's the amount of acid, is roughly equal to the concentration of Ha at the start of the reaction. So that's before anything goes. So there will be a slight difference in reality, but because the difference is so small, it's difficult to measure. We can make this approximation, this assumption. So the equilibrium law can be applied here as we have an equilibrium reaction. So we use the Ka expression to represent the reaction. So Ka is H plus A minus divided by Ha, which is at the start. Remember, the assumption that we're taking is that the concentration of Ha at the start is approximately equal to the concentration at equilibrium. So we can use this even though it's an equilibrium reaction. The units are moles per dm cubed here, and so therefore what we do is we put products over reactants. That's the equation that we use. The second assumption is that dissociation of acid is greater than the dissociation of water present in the solution. And so we can assume that all H plus ions come from the acid. Okay, so it's not coming from the water. Obviously they will exist, of course they do, because it's in solution, but we assume that they all come from the acid. And so therefore what we can assume is the amount of H plus ions is approximately equal to the amount of A minus ions. So we can now simplify this Ka expression that we've got here to something a little bit easier. So this is the good thing about chemistry, you just keep simplifying everything. It doesn't have to be complicated. So Ka is H plus squared over Ha. So basically we've just got rid of the A minus and squared the H plus. So it's a lot easier to use when it's in that format.